Good? So this is going to be my effective action, or sometimes called the Ginzburg-Landau action. Alright? Good. Usually there should be some 1 over kt over here, but I'm going to even omit that. Because really, the range of t that I'm interested in is very, very close to the critical point. Okay, in that range, the only important thing that is changing is this. Everything else is basically remaining unchanged. So the only t dependence I really care about is sitting here in this term. Okay?
So,
yeah.
I mean, you use the fact that the coefficient multiplying a should be of the form t plus tc because it has to go from positive to negative.
Correct.
So could other powers be used, or I mean,
You mean t minus tc squared and so on?
Not
Or maybe
squared,
even
but
fractional power?
yeah.
Okay. So, very important. So the point is that remember the way to think about how you got this, right? You got this by taking some finite region and then force graining it. Okay, adding up all the spins and making some giant spin out of it, right? So you haven't done anything non-analytic. So you can't get anything non-analytic, right? So it has to be only integer powers of t minus tc. For some very peculiar reason, it could happen that the leading power is missing. Okay, that's like a measure zero possibility. Okay, unless you fine-tune yourself, there are certain phase transitions where you can fine-tune it so that you approach it in a way that looks like t minus tc squared. If you do that, then of course you have to take that away. But generically, it's going to be just t minus tc. Okay?
I didn't understand that if that is some odd power of t minus tc.
It doesn't have to be odd. It's some. So the point is that there is a constant, right? And then there's a part that's proportional to t.
Well, it has to be odd because it has to change sign.
It can be anything. It's just it's some arbitrary function that changes sign.
Yeah.
It doesn't have to be odd.
So it can be used as expansion of this constant in the near OTC. Then you can just keep the fast reading there.
Precisely.
And external.
Yeah. It could be any power of t minus tc. Okay. I mean, there's a whole sequence of powers here, but really only this one matters because you're focusing
Okay.
very close to t minus tc. Okay. It doesn't have to be odd or anything like that. Okay.
So in principle, this A term could not be there also, right? I mean, in principle, you could have this T minus Tc term in lambda, for example, and you have the higher order 5-6 terms.
Very good. So there are other kinds of phase transitions. So this is the kind of phase transition which we normally associate with the second order point, right? There are other possible phase transitions where you keep this guy fixed and then you change the sign of this guy. Or even more, kind of unusually, you can keep all those fixed and change the sign of this guy. Okay, and so on. So you can look at each of these terms in this action and say what will happen if I change the sign of that. Okay? But this is what we normally call a phase transition. Okay? Those are other possibilities. They are more exotic possibilities. Okay? This one I believe will lead to a first order phase transition, which is this kind of that. Alright, other questions? So, of course, everything that we got over there, we can certainly get from here. Because all we got to do is make phi constant, and then we recover everything from there. Okay? But then we can get some more. So, let's get one more thing, actually 3 more things. And then we will go to the Ginzburg criteria. Alright, so remember that I defined for you some other exponent. So, there was an exponent called alpha. So, the alpha was defined in the following way. So, Cb is minus t squared at t squared, right? At constant b and n, but I'm going to stop writing that because we're never going to change b and n. Okay? So this guy, when you have the critical point, it behaves like b minus tc to the minus alpha. Okay, that's the definition of alpha. Alright? Then, now that we have defined this field phi, we are able to define some correlation functions. Okay? So let's ask ourselves, what is the correlation function phi of x, phi of 0? What will this be equal to? Okay? Now, we're going to look for correlation functions at very long distances. Okay? So as long as t is not equal to tc, so let's for a moment fix t bigger than tc. Okay? Then there's no average value of phi. And this correlation function should certainly vanish at long distances. Typically, in most theories, it vanishes with an exponential. It doesn't depend on the direction. It vanishes with an exponential. And there's also power sitting here, so let me write everything here. Okay? So forget for a moment what the power is. Let's focus upon this length scale that is sitting over here. This is called the correlation length. Okay, so this C is called the correlation length. And this thing diverges as you approach DC with a critical exponent called mu. Okay, this is the definition of the critical exponent mu. Okay? And finally, this thing over here, you'll see the reason for this peculiar definition over here. This theta is known as the anomalous dimension of the field form. Okay, we'll come to that later. Okay, at the moment, what we can do is using this coarse-grained theory, we can actually calculate these other quantities that we didn't calculate in the old-fashioned lattice mean field theory. Okay? So let's go ahead and calculate. But any questions about this?
So
You understand what the meaning of this is? Yeah.
that correlation length, if we increase T, if we decrease, that means that there is no order.
That's correct. So basically, it tells you the region within which spins realize that there are other spins present. So if you, so in other words, it's sort of a region where the spins like to point in the same direction, if you want. Or the likelihood of their pointing in the same direction is high.
Okay.
Okay, that's what the correlation is.
Okay. So sir, in the near the zero temperature.
Zero temperature.
Yes. Zero temperature.
Below TC.
Below TC.
Yeah. Below TC, you have to define it differently.
Oh, okay, okay.
Below TC, you have to define it as. So you have to define it as fluctuations of the spin around its average value. And then this definition still holds.
Okay, why does it said that I didn't understand? Why is that minus pi zeros?
Because what you have to do is you really have to define the average value of phi of x minus its average correlated with phi of 0 minus its average, right? But because this is an average, it doesn't depend on x. And then you do the usual thing, it comes out to this. Okay? Good? It's like some fluctuation around whatever average is. Right? That's really what you're trying to do. That is what is correlated to the correlation rate.
Okay.
All right? Other questions?
Even in TC, here it was 0, this correlation constant.
Right.
This case. But here, you also do the same thing, but it is not 0.
quite
What
the
are the
same.
things where you have
It's not quite the same.
same.
The key thing is here. Okay, this actually induces a correlation. Because previously I didn't have this term here, right? And now the term is here, and that's what will give you a correlation. Okay? So it's not exactly the same. Yeah.
Okay, actually, I have a little. So, are we considering quantum fluctuations or no?
No. This is all
Okay, this is okay.
completely classical.
Yeah, because if you do quantum fluctuation and then if you're in finite temperature, then that correlation is with Shinsates. Shinsates.
Let's don't even worry about quantum.
Yeah, okay, yeah.
There is no quantum mechanics
Yeah.
for this class, okay? This is all just classical stuff. Only thermal fluctuations. Okay? Just look at my model, okay? It had just classical spins, plus or minus. Okay? Good? All right, now, what do we want to calculate?
But this functional form is, correct only near DC. Or
Which one?
this functional form that you have written?
Yeah, it's correct only near DC.
Near DC.
Absolutely, yeah. Far away, it'll have some other form, right? But remember, we don't care far away. We're just interested in the critical
Yeah.
behavior, because far away, it'll all depend on the lattice details and stuff like that, which I don't want to worry about.
not possible, or is it not correct?
It's not even correct, far away. That's correct. So I'm not going to worry about far away. Okay? Good. So now, let's ask ourselves how we are going to compute a probability. Alright, so let me remind you of a few things. Okay? So what is this partition function? So let me write it in a form that maybe you have seen before, okay, in some other context, in the quantum context. So I'll write it like this. Okay? So this is something this is called a path integral. Okay, when you do it quantum mechanically, this is fine as path integral, but of course it's not S, but the I S over H bar. Okay, but remember, there's no H bar for us. H bar is actually the temperature. Okay, it's S over T, or E over T, or something like that. This is a Boston rate. Okay, that's what we're doing. Alright. What do I mean by this? I mean the same thing as I meant by the sum over all spin configurations. That's really all I mean. Okay, there's no time in this thing at all. It's just a sum over configurations of some Boston rate. Okay, but it's a beautiful notation because things that were discovered here in the context of phase transitions can then be translated back into quantum field theory and used over there. Okay? But for us, we won't need any of this, but this is good to know that people also write like this, just because it's so useful in the quantum field theory context. Alright, so I'm going to write it like that. And now I want to do some path integrals, or I want to do integrals over lots and lots of fields. Right? How do I do that? Well, the only integral we really know how to do is a Gaussian integral. Okay? So, by hook or crook, what we want to do is we want to reduce everything we have to Gaussian integrals. Okay, so that's the goal. So let's do that. Okay, so let's say that we would just set lambda equal to 0. Now lambda is clearly not that important for t bigger than tc, right? It's only for t less than tc that lambda becomes very important. Okay, so this is, let's say, it's maybe okay for t bigger than tc. Okay? Even then it's not really okay, as we will see later on. But let's start with that, and then we'll see what happens. Okay? Alright, if lambda is equal to 0, then you see this guy